To motivate this video lesson, I'll ask you to imagine a simple game of chance. In this game, a player rolls a fair die, and if they roll either a 1 or a 6, they receive $90. Now ask yourself, if you were on the receiving end of the payout, what's the most you'd pay to play this game? Alternatively, if you were doing the paying out, what's the least amount you'd charge someone to play? Maybe pause the video and think about it for a moment. After you do, I bet you'll say $30. That's the most I'd be willing to pay to play, and also the least I'd be willing to charge if I was on the hook for paying the winner. Why is $30 reasonable? Let's go through the line of thinking. 2/6 or 1/3 of the time, the player rolling the die will win the $90. Whereas 4/6 or 2/3 of the time, they'll win nothing. If the game was played many times, in the long run, any player would expect to win 1/3 of $90, which is $30 per game. If you pay more than $30 to play, in the long run you're doing worse than breaking even. If you flip it around and think about the game from the perspective of the person paying out the winnings, you'll see that charging less than $30 per game means you'd also be doing worse than breaking even in the long run. Here, what makes things reasonable is that people expect a certain average outcome to occur. This idea of the expectation we have about some random occurrence is the main focus of this video lesson. In this video, we'll also connect the idea of an expected value to the notion of an average occurrence. Let's talk first about how a mathematician defines the expectation of a random variable. Let's say that capital X is a discrete random variable that takes values from the finite set x1 to xn. In this case, the expectation of capital X, written e of capital X, is calculated as the following weighted sum. Here, p of x sub j is the probability mass function associated with the random variable capital X. As an example, let capital X be the payout from the game we introduced a moment ago. Capital X takes values from the set 0 and 90. If x1 is 0 and x2 is 90, then p of x1 is 2/3 and p of x2 is 1/3. Therefore, the expectation of capital X is 0 times 2/3 plus 90 times 1/3, which is, of course, 30. Just a footnote here, a discrete random variable can take values from an infinite set, in which case the expectation involves an infinite sum. Those infinite sums might converge to particular values. In fact, you've likely seen examples when you were learning about the connection between Riemann sums and definite integrals. However, it's not always true that an infinite sum will converge on a particular value. And in those cases, the expectation won't exist. Now, let's shift our attention to a continuous random variable with probability density function f of x. In this case, expectation is defined as the integral of x times f of x from -infinity to infinity. These infinities might seem strange to you, but just think of them as mathematical limits of definite integrals. We can add another footnote here that when the limits I've hinted at don't exist, then neither does the expectation. Here's an example of how to calculate the expectation of a continuous random variable capital X. Suppose the probability density function f of x is equal to 2x when x is in the unit interval, and is equal to 0 everywhere else. In this case, the expectation of the random variable capital X is calculated as the integral of x times 2x over the interval 0, 1. Here, we need to integrate over only those x values where f is positive. Evaluating this definite integral gives us an expected value of 2/3. We'll sometimes want to discuss the expectation of a function of a random variable, something like g of capital X. As you might suspect, in the discrete case, the expectation of g of capital X is calculated as this weighted sum. And in the continuous case, it's calculated as this integral. In probability theory, we often focus on the function g of x, defined as x minus the expectation of x all squared. The expectation of this g of capital X is given a special name. It's called the variance. The variance gives us a measure of how spread out a random variable will be from its expected value. A larger variance means a larger spread. Now let's see how we might estimate the expectation and variance of a random variable using data. Suppose we replicate an experiment a large number of times, and each time we do, we observe the value taken by a discrete random variable, capital X. Let's label our replicates 1 to capital K, and we'll use lowercase k to denote a typical replicate. We'll label the observations we make as d sub lowercase k. D for data, I suppose. And we'll imagine these values come from this set of lowercase x values. In keeping with our discussions from earlier videos, we'll see a given value from the set of lowercase x's pop up in this list from time to time. Let's say a particular value xj pops up in the list of observations mj times. If we take mj and divide it by the total number of replicates, capital K, then we should get a good estimate of p of xj, provided, of course, we've replicated the experiment enough times. Now, dropping the estimate for p of xj into the formula for the expectation of capital X leaves us here. This could have been calculated from the data table directly as this. This, therefore, can serve as our estimate of the expectation of capital X. It's just the sum of the right data column divided by the number of replicates. This is often called the sample mean and denoted as x bar. The very same sample mean can also be used to estimate the expectation of a continuous random variable. Justification here would simply involve splitting the range of possible x values into discrete subintervals and essentially repeating what's already been said. Our thinking also extends, in a sense, to estimates of the variance based on data. Recall that the variance of capital X is defined in terms of an expectation. Actually, an expectation of this function g of x. So, we could simply estimate the variance as the sample mean of the value taken by g of x, like this. Unfortunately, the formula presented here requires that we know the expected value of capital X. In practice, though, we only have the estimate x bar. We could sub x bar in for the expectation of capital X. It turns out that if we do that, though, we have to reduce our denominator by 1. Very loosely speaking, it's as if we've thrown away some of our experimental work by using the estimate x bar in yet another estimate. The formula here is our estimate of the variance of capital X. It's called the sample variance, and it's typically denoted as s squared. It's particularly important to consider both the sample mean and the sample variance when making comparisons between observations taken from different samples. Here's an example of what I mean. Suppose the times recorded in a half marathon for runners between the ages of 40 and 50 resulted in the following: a sample mean of 125 minutes and a sample variance of 64 minutes squared. In the same race, times posted by runners in the age 20 to 30 category resulted in a sample mean time of 107 and a sample variance of 81 minutes squared. Now, I'm a member of the older category, and my result in this race was 101 minutes. My kid ran the same race as a member of the younger category and posted a time of 81 minutes. Given all this information, whose personal result is better? If we compare my result to the average for my age category, we see that I was 24 minutes faster than the average. The same comparison, though, shows that my kid was 26 minutes faster than the average for their age category. so you might think that they're faster than me. But wait, the spread around the mean in my age category is a lot less than the spread in the times posted by the 20 to 30-year-olds. We can take that into account by dividing the difference between a personal result and the sample mean by the square root of the sample variance. The square root of the sample variance is called the sample standard deviation, or just S. For my age category, the sample standard deviation is 8 minutes. We're interested in this quantity because, as you can see, it has the same units as the sample mean. This allows us to express my result in standardized or unitless form as -24/8, or simply -3. We interpret this as me being 3 standard deviations below the mean, which is pretty darn fast, in appropriate relative terms. Now let's look at my kids' result in the same way. They've posted a -26 minutes, but when this is divided by the sample standard deviation, which in this case is 9 minutes, we find that the normalized result is about -2.89. This is 2.89 standard deviations below the sample mean. Overall, then, it seems that my normalized result is more extreme in the negative direction than the one posted by my kid. In my books, that's evidence that I'm faster. Let's recap. In this video, we defined the expectation and variance of a random variable. We uncovered formulas we can use to estimate the expectation and variance using data. We used the sample mean to estimate the expectation and the sample variance to estimate the variance. We saw, by way of example, how to compare observations from different samples in a standardized way using the sample standard deviation. This allowed us to see which observation was the more extreme. By the time you've mastered the ideas presented in this video, you should be able to do 3 things. First, you should be able to calculate the expectation and the variance of a random variable. Second, you should be able to estimate the expectation and the variance from a data set. Finally, you should be able to make a standardized comparison between observations taken from different samples or data sets, and ultimately answer the question, which of the 2 observations is more extreme? Don't just rely on this video to achieve the outcomes I've listed here. Use the exercises to practice, quiz your classmates, and read the notes. Time spent now will pay off in the long run, and as soon as in the next lesson, when we use our skills to make even more sophisticated quantitative evaluations of data sets.